Hi all. In today's class, we are going to discuss about previous year questions in organic chemistry, and we'll try to solve few questions which is having a repetitive kind of nature in exams. So we'll start with stereochemistry, and the first question we are going to solve here is finding the configuration at the chiral center. So the question is the absolute configuration at two chiral centers of minus camphor is. So this is the camphor molecule here, and we can see here two chiral carbon, that is first carbon and the fourth carbon. Now, in this molecule or in any molecule, for a carbon atom to be chiral, we have already seen it should be having four different substance like A, B, C, D. If the carbon is containing at least two same substance, then it will not be chiral. For a carbon atom to be chiral, the four substance on the carbon should be different. Okay. So here in camphor, if you are taking this carbon and this carbon, both containing three hydrogen, so it is a chiral. Now, if you are taking this carbon, it is containing same medial substance on this carbon, so it is also a chiral. No, this carbon containing two hydrogen, so achiral. This carbon also two hydrogen achiral. This carbon also two hydrogen achiral. Now this carbon, it is containing C double bond O. And this we can write it as CO, CO. That means we can write this C double bond O as two CO bonds. So this also achiral. And now this methyl, it is also containing three hydrogen, so it is also achiral. So in the molecule, the first carbon, which is containing one carbon, second, third carbon, and the fourth carbon, four different carbon atoms. This is chiral, and the fourth carbon atom, which is containing three different carbons and hydrogen, is also chiral. So in the camphor molecule, only the first carbon and the fourth carbon is chiral. And now we are going to see the configuration at these two chiral centers. We'll start with the first carbon. So to find the configuration, we have already seen, we need to number the substance at the chiral center. So in the first carbon, we need to number the substance, and we'll start with the high priority carbon and we'll number this as first carbon. So here, this carbon, it is having three hydrogen. This carbon, it is having three carbons. And this carbon, it is having one carbon, two hydrogen. This carbon, it is having one carbon and one C double bond O bond. That means this carbon is having one carbon and two oxygen. So the high priority will be this group because it is containing two oxygen. Then the high priority will be if you are taking this carbon and this carbon, it is containing one carbon, two hydrogen, but this one it is containing three carbons. That means the second priority will go to this carbon here. And the third priority, this carbon is containing one carbon and two hydrogen. This carbon it is containing three hydrogen. That means the third priority will go to this group here, and this will be the least priority group. So now we need to move from 1 to 2 to 3. That means if I am moving from 1 to 2 to 3, I am getting anti-clockwise. That means I am getting S. Now we need to look at the least priority group. That is this group. And we have already seen in a bridge molecule like this or in camphor molecule, the fourth substance in this carbon will be away from us and the fourth substance in this carbon will be towards us. This we already seen. So here also, if we are taking the same thing, here the fourth substance in this carbon, that is this medial substance, is away from us. So the least priority group is away from us. So we can take the S as the configuration of first carbon. Okay. So 1s will be the answer. So the answer is either C or D. Now we'll go to the fourth carbon here. Here also we need to assign the priority. So here we are having three carbons and one hydrogen that is coming towards us. So there is a hydrogen which is coming towards us. And if we have hydrogen in a carbon, it will be having the least priority. So this will be having the least priority. Okay. So the hydrogen got the least priority. Now we need to find which is having highest priority. We have one carbon here, and the third carbon here. And this carbon, it is attached to three other carbons. This carbon, it is attached to one carbon and two hydrogen. This carbon, it is attached to two hydrogen and one carbon. So that means this carbon, which is attached to three carbons, will get the high priority. So this will be the high priority group. Now this got the high priority because it is attached to three carbon atoms. Now we need to decide between this and this to find which is having second priority. Now this carbon is containing one carbon and two hydrogen. This carbon also containing one carbon and two hydrogen. So in this case, what we'll do, if the chiral atom is attached to same carbon like this, we'll move to the next atom to find out the priority. So now we are going to this carbon to find the priority. That is this carbon and this carbon. Okay. Now this carbon, it is attached to two oxygen. and one carbon, but this carbon it is attached to two hydrogen and one carbon. That means this carbon is having high priority. That means this group is having high priority. Okay. So the second priority will go to this carbon and this will be the third priority group. Now again we need to move from 1 to 2 to 3. So if I am moving from 1 to 2 to 3, what I'll get? I am getting clockwise rotation. That means I am getting here R. Now we need to look at the least priority group, that is the hydrogen. It is coming towards us. So if the least priority group is coming towards us, we need to change the R to S. So we are getting in first carbon the configuration as S, so 1s. And in fourth carbon also we are getting the configuration as S. So the configuration is 1s and 4s. So the answer will be 1s and 4s. The answer will be T. Now if we are moving to the second question, here also we can see the same type of question, that is finding the configuration at the chiral center. And in this molecule also we can see there is only two chiral centers, that is this carbon and this carbon. And here also this carbon is numbered as first carbon and this is numbered as fourth carbon. And we need to find the configuration at both chiral centers. So we'll start with the first carbon here. Now, if you are assigning the priority of the substance in this carbon, we can see this carbon, it is attached to 3 hydrogen. This carbon, it is attached to 1 carbon and 2 hydrogen. Here, this carbon, it is attached by C double bond C. That means this carbon is attached by 2 carbons and a hydrogen. Now, this carbon, there is a C double bond O. That means this carbon is attached by 2 oxygen and a carbon. So now out of all these carbon, this will get the high priority because it is attached to 2 oxygen. Now the second will be this carbon because it is attached to 2 carbons and a hydrogen. This one is attached to 1 carbon only. So this will get the second priority. And now between this carbon and this carbon, this is attached to 3 hydrogen, but this is attached to 1 carbon and 2 hydrogen. So this will get the third priority. And methyl will be the least priority group. Now if you are moving from 1 to 2 to 3, we are getting clockwise and the least priority group is away from us. That means from clockwise we will get R configuration for first carbon. So we are getting 1R. Now we are going to find the configuration at the fourth carbon here, that is this carbon. And now in fourth carbon we can see a hydrogen. So if we are having a hydrogen in a chiral carbon, it will get the least priority. So it will get the fourth priority. Now we are having 3 carbons here. And this carbon is attached to 2 hydrogen and 1 carbon. This carbon again C double bond C. That means this carbon is attached to 2 carbons and a hydrogen. This carbon, it is attached to 1 carbon and 2 hydrogen. So out of all these, this carbon which is attached to 2 carbons will get the highest priority. So this is having high priority. Now we need to decide between this carbon and this carbon. Both attached to 1 carbon and 2 hydrogen. This also attached to 1 carbon and 2 hydrogen. So in this case, what we'll do, we'll move to the second atom here. Second atom means next to this carbon atom will move. And here, next to this carbon atom will move. So now we need to assign the priority by looking at this carbon and this carbon. Now, this carbon, it is attached to 1 carbon and 2 hydrogen. But this carbon, it is attached to oxygen by a double bond. That means this carbon is attached to 2 oxygen. So if you are comparing this carbon and this carbon, this is getting high priority. That means this carbon will get high priority compared to this carbon. So the second priority will be this carbon due to the presence of oxygen on this carbon. And this will be the third priority group. Now we need to move from 1 to 2 to 3. That means if you are moving from 1 to 2 to 3, we are getting anti-clockwise, we are getting S. But here if you are looking at the fourth priority group or least priority group, it is coming towards us. So the S will change to R in this case. So the configuration at the fourth carbon will be 4R. So overall, the configuration at this molecule will be 1R and 4R. So the answer will be A, that is 1R and 4R. So this is the first type of question we can expect in stereochemistry, finding the configuration at the chiral centers. Now we are going to look at second type of question that we can expect from stereochemistry, that is finding out the relation between two atoms in a molecule. So we have already seen two atoms in a molecule. They can be either homotopic or enantiotopic or diastereotopic. And there is one more case, they can be also constitutionally heterotopic. Here, this will come when two atoms that we need to find the relation is having different connectivity. But in most cases, we'll expect these three. In exams, most probably homotopic, enantiotopic, diastereotopic questions will come. This constitutional heterotopic case is very rare in exam. So we'll expect these three in exam. Okay. So to find whether two atoms are homotopic, what we need to do? We need to look for C2. If two atoms are related to each other by C2, then these two atoms are homotopic. And if there is no C2 and these two atoms are not related by C2, then it will not be homotopic. In this case, only will come to enantiotopic and diastereotopic case. In this case, we'll find whether there is a sigma, and if this sigma is bisecting these two atoms, we'll get diastereotopic, and if this sigma is reflecting both these atoms, we'll get enantiotopic. I hope you remember this. One more time I'll say, suppose in a molecule, to find whether two atoms are homotopic or not, we'll see whether there is a C2 in the molecule, and if these two atoms are related to each other by C2. If these are related to each other by C2, then these two atoms are homotopic. And if there is no C2 in the molecule, then these two atoms are not homotopic. In this case, we'll consider whether they are enantiotopic or diastereotopic. For this, we'll look for sigma. If there is a sigma in the molecule, and if two atoms are getting bisected by the sigma, that means these are diastereotopic. But if these two atoms are getting reflected by sigma, that means these two atoms are enantiotopic. Okay. And one more case, suppose there is no sigma in the molecule at all. In this case also, you'll get diastereotopic. Okay. So we'll come back to our molecule. Here we need to find the relation between HA and HB and Br1 and Br2. And here the connectivity of HA and HB is same. So this will not be constitutionally heterotopic. And Br1 and Br2 also, it is connected to same kind of atoms. So this also not constitutionally heterotopic. Now we need to find whether they are homotopic, enantiotopic or diastereotopic. In homotopic case, there should be a C2 in the molecule. Suppose you are doing a C2 in the molecule, what will happen? Here, this HA will come here, HB will come here. Both are hydrogen. So there is no problem on this carbon. Now in these two carbon, after doing C2, the methyl group, it will come below the plane after doing C2. Because if you are doing C2, what will happen? Both this group will come below the plane and both this bromine will come above the plane like this. So after doing C2, both bromine will be above the plane like this. So now after doing C2, if you are comparing this molecule with this molecule, you can see this not at all similar. Because here we are having both bromine below the plane, but here both bromine above the plane, and methyl also the configuration is changed. That means in this molecule there is no C2. That means these two atoms are not homotopic. Now we'll see whether they are enantiotopic or diastereotopic. And for this, we'll see whether there is sigma in the molecule. And we can see there is a sigma in the molecule like this here. Suppose I'm drawing the molecule like this, and I'm having two hydrogen here. One is HB and second one is HA. And in this carbon, I'm having Br1, here also Br2, and there is a methyl group here, there is a methyl group here. In this molecule, we can see a mirror plane like this. Okay, there is a mirror plane in this molecule, and this mirror plane, it is bisecting HA and HB. So if a mirror plane is bisecting two atoms, that means these two atoms are diastereotopic. So HA and HB is diastereotopic. So here HA and HB is enantiotopic. This option is wrong. In option B, HA and HB is diastereotopic. So it can be right. Again, C, HA and HB is diastereotopic. It can also be right. In D, HA and HB enantiotopic. So this is also wrong. Okay. So answer can be either B or C. Now again, if you are coming back, again we are having a sigma here. And this sigma, it is reflecting both Br1 and Br2. So if a mirror plane is bisecting two atoms, that means these two atoms will be enantiotopic. So Br1 and Br2 is enantiotopic. So if you are coming back to the options, in option B, we can see Br1 and Br2 is enantiotopic. So the correct answer will be option B, where we can see HA and HB is diastereotopic and Br1 and Br2 is enantiotopic. Okay. So the second type of question will be finding the relation between two atoms in a molecule. Here first we'll see whether it is homotopic by looking for C2. If there is no C2 in the molecule, then we'll look for a sigma. And if two atoms are getting reflected by sigma, that means they are enantiotopic. And if two atoms are getting bisected by sigma, that means they are diastereotopic. Okay. And now we'll see one more example for this type of question. Suppose in this molecule, you need to find the relation between HA and HB. So here also the first thing we have to do is finding out whether they are homotopic or not. So for that, we need to find whether there is a C2 in the molecule and these two atoms are relating to each other by C2. And suppose we are doing a C2 in this molecule like this. So after doing C2, what will happen? Both these phenyl rings, after doing C2, it will go below the plane. Okay. So that means this molecule is not having a C2. So these two atoms is not homotopic. So the next probability is whether they are enantiotopic or diastereotopic. So for that, we will look for presence of sigma or mirror plane in the molecule. And here also we can see a mirror plane in the molecule like this. And now in the molecule, we are having a mirror plane because both these phenyl rings are above the plane. And here you can see this mirror plane is reflecting both He and Hb. That means if a mirror plane is reflecting two atoms, these two atoms will be enantiotopic. So here the Ha and Hb will be enantiotopic. So the answer will be C. And the second type of question in CD chemistry will be finding relation between two atoms. And first we'll see whether they are homotopic or not. For that, we'll look for the presence of C2. If there is no C2, that means this will not be homotopic. In this case, we'll consider enantiotopic and diastereotopic. And in this case, we look for sigma. If sigma is reflecting both atoms, that means they are enantiotopic. And if sigma is bisecting, it will be diastereotopic. And if there is no sigma in the molecule, then also it will be diastereotopic. Okay. So this is how we'll find the relation between two atoms in a molecule. So this is the second type of question in stereochemistry. And the next type of question that we can expect in stereochemistry is finding out the IUPAC name for a given organic molecule. Suppose we have an organic molecule like this and you need to find the IUPAC name. For that, we don't have to remember all the IUPAC rules for naming. Instead, if you're having a serious center in the molecule, we can find out whether it is having R or S configuration. And also, if you're having an alkene in the molecule, we can find out whether it is having E or Z configuration. From this, easily you can find out the name from the given options. So in this molecule, we can say chiral carbon here because it is attached to 4 different groups. Here, this carbon and this carbon is different because this carbon is attached to 3 hydrogen, this attached to 1 double bond and 1 hydrogen. And the third group is OH group, and here oxygen is attached to carbon. And the fourth group here will be hydrogen. And here you can see 2 bonds are already in the plane of paper. One is away from us. So the fourth bond will be towards us. And here the fourth bond will be hydrogen. If nothing is mentioning in a carbon, that means that bond will be hydrogen. Okay. So now if you're finding the stereochemistry in this carbon, you need to assay the highest priority group as first priority. Here, the oxygen is having high priority than carbon. So OH will get first priority. And if we are having a hydrogen in the carbon, always it will get the least priority. So it will get the fourth priority. And now we are having 2 carbons. Here this carbon having 3 hydrogen. This carbon is having a double bond. That means 2 carbons and a hydrogen. So this carbon will get the second priority and this will get the third priority. And now we'll move from 1 to 2 to 3. We are getting clockwise. That means we are getting R. But the least priority group is coming towards us. That means we need to change the R to S. So the configuration on this carbon will be S configuration. And now if we are looking at the options, in option A, 2R, option B, 2S. So we already got it as S. So option A we can eliminate. And option C also we can eliminate because here we are having R instead of S. And now we need to find whether this alkene is E or Z. Then only we can find out whether B is the answer or D is the answer. Okay. Here E and Z means cis. And if you're finding difficulty in assigning E and Z, you just remember that Z means cis. Okay. So this Z is corresponding to cis. So if Z is cis, that means E will be trans. So to remember this E and Z, you remember Z as cis. So if Z is cis, that means E will be trans. And in our molecule, we are having a double bond here. And both the high priority group or carbon is away from each other. That is opposite direction. So this is trans. And one more way we can look. We can put a hydrogen here in this carbon. And we can put a hydrogen in this carbon also. And if you are looking at the direction of both hydrogen, both are opposite to each other. That means again, this is trans. So trans means this configuration will be E. And if I have numbered this molecule, this is the first carbon, second carbon, third carbon. In the second carbon, we are having 2S. And the third carbon, we are having a double bond, which is having E as the configuration. So the answer will be 2S, 3E. So in the given options, the answer will be D because we are having 2S, 3E here. So the answer is D. Okay. So like this, you can find out the name of an organic molecule just by looking at the configuration of the chiral carbon. And if you are having an alkyl, we can find out whether it is E or Z. Okay, Z means cis. And this is the third type of question that we can be expected from stereochemistry, that is finding out the IUPAC name for the organic molecule. And now we'll see the next type of question that we can expect in stereochemistry, that you'll be getting two molecules and you need to find the relation between both these molecules. They can be either identical, enantiomers, diastereomers, or constitutional isomers. And we already know what all these terms means. Identical means both these molecule will be exactly similar. Enantiomers means both these will be mirror image of each other. Diastereomer means both these will be not mirror image. Okay, if they are not mirror image, we will call it as diastereomers. And constitutional isomer means here the connectivity of groups in two molecules will be different. And if you are getting a question like this, what we'll do first is that we'll determine whether they are identical or not. If they are not identical, in this case only we'll move to the enantiomer and diastereomer case. Okay, so first we have to determine whether they are identical or not. So for that, we'll consider the rotation in the molecule. So why we are rotating the molecule? Because here we have given the three-dimensional structure of molecule. And we already seen in previous classes, if we are having a three-dimensional structure, we can rotate the molecule at any angle we want. In this case, it will not change the structure of molecule and the configuration in the molecule will be same. Okay. But in case of Fisher projection, Fisher we know it is a 2D projection. Here we can only rotate this in plane of paper, that too in 180 degree. If you are doing any other rotation in this molecule, the configuration of this carbon and this carbon will be different. But in case of three-dimensional structure, we can rotate the molecule at any angle. It will not change the structure of molecule. So here also we can see the three-dimensional structure of molecule. That means just by rotating the molecule, the structure of molecule or the configuration of molecule will not change. So just to find the relation between both these, we can rotate any of this molecule. Okay. So first we need to find whether they are identical or not. So for this, you can rotate any of this molecule, and just by rotating a molecule, if you are getting the same structure as a second molecule, that means both these molecule will be identical. So to see whether they are identical or not, suppose I am rotating the second molecule here and I am rotating this molecule in 180 degree. That means I am doing a C2 rotation here. What will happen? All the right substance, that is this bonds which lies in the right side, after rotation, it will come to the left side, and all the left substance, that all these substance after rotation, it will come to the right side. So suppose I am drawing all the right substance, that is this all substance after rotation in the left side. Here we are having a CH bond also, and after rotation, this bond, it will come to here. So we are getting it here, and this bond after rotation, it is coming here. Okay, so we are having a bond here. Now after rotation, all the left substance, that is these two bonds and this bond, it will come to the right side. So I am drawing these two bonds here and this carbon-carbon bond here in the right side. And after rotation, this CH bond and this CC bond, this will also come in the right here in this carbon, and this CH, it will come here after the rotation. So in this carbon, there will be hydrogen and there will be an Me after the rotation. So now this is the product you will get after doing a C2 rotation in the second molecule. Now if you are compare this molecule with the first molecule, we can see here in the first molecule also, all these things are exactly similar after doing a C2 rotation in the second molecule. So just by doing a C2 rotation in the second molecule, we are getting the first molecule. That means both these molecules are identical or similar. So the correct relation between the following structure is that the answer will be A. They will be identical, because just by rotating second molecule in 180 degree, we are getting the first molecule from the second molecule. That means both these are identical molecule. And now we'll see a similar question. The two compounds given below are. Here also we have given two molecules and we need to find the relation between both these. We need to find whether they are enantiomers, identical, diastereomers, and regioisomers. Here regioisomer means it is a type of constitutional isomer. That means the connectivity of functional group in two molecules will be different. So the regioisomer, if you are seeing in question, just understand that it is a constitutional isomer. Okay. And here we need to find the relation between this molecule and this molecule. So in any case, first we'll see whether they are identical or not. Then only we'll move to the other case. And to find whether two molecules are identical or not, we need to do the rotation in the molecule. And just by rotating any of the molecule, if you are getting the second molecule, that means both these will be identical molecule. Okay, so suppose I'm rotating this molecule here, that too in 180 degree. So here, suppose I'm rotating this molecule in 180 degree, or I'm doing a C2 rotation. What will happen? All the groups, the right side of this will come in the left side, and all the left side substituent after rotation, it will come the right side. So I'm writing the product after rotation here. Now, all these bonds in the right side before rotation. So after rotation, all these bonds will come in the left side. Okay. Now, for this bond, which is in the axis of rotation, there will be no change. So we can draw this bond here. Now, this bond, which lies in the left side before rotation, will come in the right side after rotation. Okay. And we need to mention this methyl group and hydrogen also. Suppose we are doing a C2 here. All the upper substituent after doing C2, it will go below the plane. So, since hydrogen is above the plane before rotation, after the rotation, it will come below the plane, and here M is below the plane before rotation. So after C2, it will come above the plane. Now Me will come here. And we are missing carbonyl. Here we are having a carbonyl in this carbon. And this is the product of C2 in this molecule. Now if you are comparing this molecule with the first molecule, we can see these are exactly similar. So just by doing a C2 in the second molecule, or just by rotating the second molecule, we are getting the first molecule from the second molecule. That means both these are identical. So the answer will be B. These will be identical molecules. Okay. And now we'll see one more example in the same concept. The correct relation between the following compounds is. So these are the two compounds that we need to find the relation. So here also, the first we need to see whether they are identical or not. Then only we'll move to the other case, and to find whether they are identical or not, we need to do the rotation. Okay, just by rotating the second molecule, if you are getting the first molecule, that means they are identical. If you are not getting the first molecule from the second molecule after rotation, that means this will be either diastereomers, enantiomers, or constitutional isomers. That we will see next. So first we'll check for the possibility of identical molecule. Okay, so suppose I am rotating this again in 180 degree. What will happen? So this is the rotation axis. I am rotating this in 180 degree. So after rotation, all the left substituent will come in the right position and all the right substituent will come in the left side. Here, this lies in the axis. So for this, no change. And all these bonds which lies in the right side will come in the left side now. And here we can see a chlorine below the plane and hydrogen above the plane. And after rotation, the below the plane substituent will come in the above plane. So here chlorine will come above the plane, and hydrogen, since it was above the plane before rotation, now it will come below the plane. Okay. And now we look at the left side. We can see here also a C double bond C. After rotation, it will come in the right side. And here also, we are having two bonds. This CH bond and there is a CC bond. And these two substance here, it lies in the plane of paper. So after doing rotation also, it will be same. It will be in the plane of paper. Hydrogen will be here and the CC bond will be here. So we can draw the CH here and there is a CC here. And in this carbon, we can see a methyl group in the plane of paper. So that methyl will be here. And now we are having a substance. Before the rotation, it was below the plane. So after the rotation, it will come above the plane. So OH will come above the plane. So just by rotating the second molecule in 180 degree, we are getting this. So here we can see this is exactly similar to that of first molecule. So that means this molecule and this molecule is exactly similar. That means they are identical. So the answer will be C. They will be homomers or identical. So if you are getting two molecules like this in exam and we need to find the relation between both these molecules, first we will consider whether they are identical or not. And to see this, we will rotate any of this molecule. And after rotation, if you are getting the same molecule, it will be identical. In three cases that we considered here, everything was identical. But suppose you are not getting the same molecule after rotation, then it will be either enantiomers or diastereomer or constitutional isomer. Here, enantiomer means you can find the stereochemistry in the molecule. If suppose you are having one chiral carbon and it is R, and the next molecule here the stereochemistry of this chiral carbon is S. That means R is converting to S. Or suppose in the first molecule you are having RR, but in the second molecule it is converting to SS. Suppose in the first molecule you are having SR, but in the second molecule it is converting to RS. In all these cases, it will be enantiomer. Okay. And if we are not getting enantiomer, then it will be diastereomer. Diastereomer means here also you find the stereochemistry at the chiral carbon in the molecule. Suppose you are having RR in first molecule, but in the second molecule only the configuration of one changed. That means if you are getting either RS or SR, in both only one configuration changed. That means this molecule and the second molecule will be diastereomer with each other. Okay. And constitutional isomer means here if you are looking at the connectivity of different groups in two molecules, it will be different. So if the connectivity of group is different in different molecule, that means both these will be constitutional isomers. Okay. So in exam, if you are getting a question to find the relation between two molecules, first consider the case of identical molecule. If they are not identical, then only move to the enantiomer, diastereomer, and constitutional isomer case. Okay. And now we are moving on to next chapter, that is aromaticity. Here we'll discuss a few questions on aromaticity chapter. So the first question is the compound that is anti-aromatic is. So we have given four compounds and we have to find the compound which is anti-aromatic. And we have seen for compound to be aromatic, it should be slightly planar conjugated and it should be containing 4 and plus 2 pi electron. Okay. This is the condition to be aromatic. And for a molecule to be anti-aromatic, the first three cases same. It should be cyclic planar conjugated, but instead of 4n plus 2 pi electron, it should have 4n pi electron. Okay, here it will be anti-aromatic. And in question, you need to find out of all these four common, which is anti-aromatic. And now we'll see each case. In first molecule, we can see there is totally 2 pi bond. That means there are total 4 pi electron. And there is a boron, and we have seen in boron there is a vacant p orbital, and this can participate in delocalization. So it is a conjugated system which is having continuous conjugation of pi electron. But here boron is electron deficient. It cannot donate any electron to this pi delocalization. So the total number of pi electron here will be 4 pi. So it is cyclic and it is planar because all the atoms in the molecule is sp2 hybridized. So if all the atoms are sp2 hybridized, we can see it is planar. And then it is conjugated and it is containing 4 pi electron. So the compound A is anti-aromatic. So the answer is option A, 1. And now we'll see in case of other three molecules also why it is not anti-aromatic. We'll see. In second molecule, here we can see this carbon, it is sp3 hybridized. And here also this carbon also sp3 hybridized. And if you know molecule, if you are having one sp3 hybridized atom, that means it will be non-aromatic. So the second compound here is non-aromatic. And the third compound, here also we can see an sp3 hybridized atom. So this is also non-aromatic. And in the last molecule, here this carbon oxygen double bond is polar. Here, due to the high electronegativity of oxygen, this can move to the oxygen. So after this bond delocalization, there will be a negative charge on the oxygen, a positive charge on the carbon by the movement of this pi electron to the oxygen. Okay. So if we are getting a molecule like this, a 3-membered ring which is containing one pi bond and one positive charge. Now all of the carbons in this 3-membered ring became sp2 hybridized. So it is cyclic planar conjugated. And now the total number of electron here is only these 2 electron. So 2 electron, it is a part of 4n plus 2 pi system because when n is equal to 0, 4n plus 2 will become 2 electron. So here the last molecule, it is containing cyclic planar conjugated system which is containing 2 electron which is part of 4n plus 2 system. So this will become aromatic. In our question, we need to find the anti-aromatic compound. So the option 1 will be the correct answer. And now we'll move to the second question in aromaticity. That is, among A to C compound, the aromatic compounds are. So we have given 3 compounds here. And we need to find the aromatic compound in between these 3. And we have already seen this molecule in aromatic chapter. Here we can see it is a molecule containing 10 carbon. And there are total 1, 2, 3, 4, 5. There is total 5 pi bond. That means there are total 10 pi electron. And 10 pi electron means it is a part of 4n plus 2 system. When n is equal to 2, the 4n plus 2 will become 10 electron. So if you are looking at this molecule, we can see all the carbon atoms are sp2 hybridized, and it is a cyclic molecule. And since all are sp2, it is planar and it is conjugated, and it is containing 4n plus 2 pi electron. So we may think it is planar, but we have already seen this molecule. Here there are 2 hydrogen atoms in this molecule, and due to the steric interaction of these 2 hydrogen here, it will become non-planar. And if any of the condition for a molecule to be aromatic, that is cyclic, planar, conjugated, and 4n plus 2. If any of this condition is lost, in that case, that molecule will become non-aromatic. Here also, due to the steric interaction between these 2 hydrogen here, what will happen? The planarity of the molecule will be losing. So after losing the planarity, this molecule will become non-aromatic. So the first molecule here is non-aromatic due to the steric interaction between these 2 hydrogen. Okay. Now, in the next molecule, we can see these 2 hydrogen is removed by an oxygen bridge. So if you are removing this hydrogen by a oxygen bridge or any other bridge, in that case, this molecule will become planar now. So in this case, now we can see it is cyclic, and now it became planar because we removed both this hydrogen by some other atom, and it is conjugated, and it is containing 4n plus 2 pi electron, that is 10 pi electron. So this molecule become aromatic. And now if we are coming to the third molecule here, we can see it is a cyclic molecule, and all the atoms in the molecule is sp2 hybridized. So it is planar, and it is containing alternate single and double bond. So it is conjugated. So it is cyclic, planar, conjugated, and it is containing total 1, 2, 3, 4, 5 pi bond. That means 10 pi electron. It is an example of 4n plus 2 system. So this molecule here is, it is cyclic, planar, conjugated, and it is containing 4n plus 2 pi electron. So it is aromatic. So C also aromatic. So out of A, B, C, we got A is non-aromatic due to presence of these 2 hydrogen, and B and C are aromatic. So the question is the aromatic compounds among A to C are. So the answer will be B and C. So the option C will be the correct answer. B and C only the aromatic compound among the given 3 compounds. So now we'll move to the next question from aromaticity. That is, among the carbocations given below, that is among these 3 carbocations, which one is homoaromatic, which one is anti-aromatic, and which one is aromatic? So one among these is aromatic, one is anti-aromatic, one is homoaromatic, and we have to find out which belongs to which category. And this molecule here, that we have already seen this molecule contains 1, 2, 3, 4, 5, 6, 7, 8. Total 8 carbon atom. And out of this, one is sp3, and there is 1 carbocation, and there is 3 pi bond. And here we have seen this molecule. It can act as aromatic molecule just by surpassing this sp3 hybridized atom. And normally we have seen if in a molecule sp3 hybridized atom is there, that will become non-aromatic. So we'll expect this molecule to be non-aromatic. But in this case, this sp3 will move above the plate. So in this case, all the other carbon atom will come in the plate, and the remaining part of this molecule acts as an aromatic molecule. So this 8-membered ring, 1 carbon will move above the plate. That is the sp3 hybridized carbon will move above the plate, and the remaining carbon atom, that is total 7 carbon atom. 1, 2, 3, 4, 5, 6, and 7. So 7 carbon atom will remain in the plane, and there will be 1 positive charge, and there is 3 pi bonds. And now in the molecule, we can see a positive charge and 3 pi bonds. And now the total number of pi electron here is 6 pi electron, which is an example of 4n plus 2 system. And now this molecule is cyclic, and now it is planar because all the atoms in the plane is sp2 hybridized, and we can see alternate single and double bond, and there is a carbocation. So it is conjugated also. So the first 3 criteria, that is cyclic, planar, conjugated, satisfied, and it is containing total 6 pi electrons. So it is 4n plus 2 system also. So now the molecule became aromatic just by surpassing a sp3 hybridized atom. Just by moving the sp3 hybridized atom above the plane, now we got an aromatic molecule. This molecule, we'll call it as homoaromatic molecule. So the molecule A will become homoaromatic. So in option A, we can see A is homoaromatic. And in option D also, we can see A is homoaromatic. So the answer is either A or D. Okay. And now the compound B, here we have total 1, 2, 2 pi bond. So that means total 4 pi electron. So from here itself we can see it is an example of foreign system. And now we look at the other criteria for a molecule to become anti-aromatic, that is cyclic planar conjugated. Here this molecule is cyclic and all the atoms here is sp2 hybridized. So it is planar and is conjugated because it is containing 2 pi bond and a carbocation. So the first three criteria satisfied, cyclic planar conjugated, and is containing 4 and pi electron. So the B molecule here is, it is anti-aromatic. Okay. So in option A is homoaromatic, B is anti-aromatic. In option D, B is aromatic. So the option D is wrong. So the correct answer will be option A. That is A is homoaromatic, B is anti-aromatic. Now we'll see in case of C also to confirm the answer. In C, we can see there is a 3-membered ring. It is containing 1 pi bond and 1 carbocation. Here it is cyclic and here all the carbon atoms are sp2 hybridized, so it is planar, and it is conjugated because it is containing 1 double bond and 1 carbocation. So it is cyclic, planar, conjugated, and the total number of electron here is 2 electron, which is example of 4n plus 2 system when n is equal to 0. So it is 4n plus 2 system also. So it is cyclic, planar, conjugated, containing 4n plus 2 pi electron. So it is aromatic. Okay, so here the correct option will be option A, where A is homoaromatic, B is anti-aromatic, and C is aromatic. And now we discussed 3 questions from aromatic chapter. Now we'll move to the next chapter, that is organic spectroscopy. And here the first question is, in the broadband decoupled carbon-13 NMR spectrum, the number of signals appearing for the bicyclooctane A to C respectively are. So we have given here 3 compound and we need to see the number of signals in carbon-13 NMR spectrum. And don't confuse yourself with this broadband decoupled carbon-13 NMR. Here broadband decoupled means we will give continuous radio frequency. So here the coupling will be low. We have seen if a NMR active nuclei, suppose a carbon-13, which is NMR active, is adjacent to another carbon-13. In this case, we have seen a coupling can happen, right? In other case, suppose the carbon-13 nuclei is adjacent to a proton nuclei. Here, this also NMR active, this also NMR active. So, here a coupling can happen between these two. Here also coupling can happen. So to remove this coupling, because if coupling is present, the spectrum will become too complex and it will be very difficult to interpret the spectrum. So to remove the coupling between this NMR active nuclei, what we'll do, we'll give the continuous radio frequency. So that's what I mean by this broadband decoupled carbon-13 NMR. You just understand that in broadband decoupled carbon-13 NMR spectrum, the coupling will be very less. Okay. Here you don't have to see the coupling details. You only need to find out number of signals corresponding to each of this molecule in carbon-13 NMR. So first we look for the first molecule here, and to find out the number of signals in carbon-13 or in proton NMR, what we'll do, we'll find out the mirror plane in the molecule. So in this molecule, we can see there is a mirror plane here, and we can see one more mirror plane. There is also a mirror plane. So in this molecule, there are 2 mirror planes, one mirror plane here and one mirror plane here. And now we are going to see the number of signals here. So if you are looking at this mirror plane first, we can see this carbon and this carbon, which is reflecting by this mirror plane, will have same signal. So you'll get one signal corresponding to this carbon and this carbon. Okay. And now suppose we are looking at this mirror plane here. Now this is reflecting this carbon and this carbon. That means both this will have the same signal. So for this carbon also, we'll get the same signal. And in this left side, we can see this mirror plane is reflecting this carbon and this carbon. So this carbon will have the same signal corresponding to this carbon. So now we got one signal corresponding to 4 of this carbon. And suppose we are looking at this mirror plane again. One more time. Here you can see this mirror plane is reflecting this carbon and this carbon. So these two will have the same signal here. And we'll get the second signal corresponding to these 2 carbon. And there's 2 carbon remaining in the molecule, this and this, and it is getting reflected by this mirror plane. So it will have the same signal. So you'll get the third signal corresponding to these 2 carbon. So total from this molecule, 1, 2, 3. You'll get 3 signals from this molecule in carbon-13 NMR. Okay. So in options, you can see option A, 5, 3, 5, 3. So the option A we can eliminate and option C also we can eliminate. So the remaining is option B and option D. both containing for compound A 3 signals. And there is one more way to find out number of signal other than finding out by mirror plane like this, because if you are finding out number of signal like this, it may take so much time. So instead we can find out number of signal without the mirror plane just by looking at the molecule. Here in the molecule you can see this carbon atom, and this carbon atom is having similar chemical environment because both is bonded to 3 other carbon atom and 1 hydrogen atom. So we can think both this carbon will have the same signal in carbon 13 NMR. Now this carbon atom, if you are comparing with this, it is having same chemical environment because this also bonded to this carbon and one other same kind of carbon. So now this and this is having same signal. And now in this side also, if we are comparing with this carbon and this carbon, we can see this and this also having the similar chemical environment. So these two carbon also having the same peak we can consider. And now this carbon here and this carbon here, both this bonded to same chemical environment carbons. So this also will correspond to the same peak. Okay, so now total from molecule we got 1, 2, 3 peak. Okay, and now if we are following the same thing in this molecule also, here we can see there is 2 carbon atom in the bridging position and both these will have the same peak. So first peak you'll get from these 2 bridging carbon atom, and now this carbon and this carbon both is having same chemical environment because both is attached to the same type of carbon. So both this will correspond to the same peak. And now if you're looking at this side, these two carbon also having the same chemical environment, and this chemical environment is similar to these 2 carbon atom. So that means this carbon is also corresponding to the same peak as of this carbon atoms. And now these 2 carbon also having the same chemical environment as of these 2 and these 2. So this will also correspond to the second peak. So totally from this molecule, we'll get first peak corresponding to these 2 carbon and the second peak corresponding to these 6 carbons. Okay. So total from this molecule, we'll get 2 peaks. So in option B, 2, and in option D also 2. So we cannot decide from this molecule. And now also we need to decide between B and D. And now in option C, we need to find out the number of signal to find out the answer. Here, again, this carbon and this carbon, which is bonded to 3 other carbon, and it is having same chemical environment. So it will have the same peak in carbon 13 NMR. And now this carbon, which is attached to these 2 carbon, will have a peak in carbon 13. And there is no other carbon in the molecule which is having similar chemical environment as of this carbon. So this peak will be corresponding to this one carbon. Okay. And now if you are comparing this carbon and this carbon, we can see both are same chemical environment. So this will correspond to the next peak. Okay. And now if you are taking this carbon and this carbon, both is having same chemical environment because it is attached to the same carbon in the left side and also in the right side. So that means this carbon and this carbon is having same chemical environment. So same peak. So this will correspond to the same peak. And these 2 carbon is not equivalent to these 2 carbons because compared to both this carbon, this chemical environment is different. Okay. And now this carbon here, it is having a peak, and there is no other carbon which is having the same chemical environment as of this carbon. And now in total from this molecule, we got first peak corresponding to this carbon and the second peak corresponding to these 2 carbons and the third peak corresponding to these 2 carbons, fourth peak corresponding to these 2 carbon and the fifth peak from this carbon. So total there will be 5 peaks from this molecule in carbon 13 NMR. So the answer will be 3, 2, 5. So the correct option is option B. Okay. Now we'll move to the next question from organic spectroscopy. That is, in the mass spectrum of dichlorobenzene, the ratio of peaks at M by Z of 146, 148 and 150 is. So here, suppose we are taking this as M peak, the difference between 146 and 148 is 2. So this will become M plus 2 peak. And if 148 is M plus 2, 150 will become M plus 4 peak. Because the difference between 146 and 150 is 4. So if 146 is corresponding to M peak, 150 will be M plus 4 peak. And now we need to find the ratio of all these peaks. So in the molecule, that is dichlorobenzene, we have 2 chlorine. And we need to find out the ratio of isotopic peaks of these two chlorine. So now we are taking chlorine, 2 chlorine the molecule, and we already know chlorine having two isotopes, chlorine 35 and chlorine 37. And both this chlorine can be any of this isotope. The second chlorine also can be chlorine 35 or chlorine 37. And the ratio between both these isotopes is 3:1. Here also the ratio between chlorine 35 and chlorine 37 is 3:1. And now we need to find the ratio of M peak and M plus 2 peak and M plus 4 peak in the molecule. So to get the M peak from 2 chlorine, what should be the scenario? Both chlorine should present in the 35 isotopic form. Then only you'll get the M peak from the mass spectrum. Okay, so M peak you'll get when both chlorine present in the 35 isotopic form, and M plus 2 will get, there is two probability for M plus 2 to happen. Either the first chlorine can present in the 37 form and the second will present in the 35 form. Here you'll get M plus 2 because from here to here a plus 2 increased. Okay, and there is one more probability. The first chlorine can be chlorine 35, but if the second chlorine is present in the chlorine 37 form, here also you'll get the M plus 2 peak. Okay, now for the M plus 4 peak, both chlorine should present in the chlorine 37 form. And how to find the intensity ratio between all these? We'll multiply the ratio of first chlorine isotope with the second chlorine isotope. Like that, we'll find the intensity. Now the relative ratio of chlorine 35 is 3. So we'll multiply 3 into the ratio of second chlorine, that is chlorine 35. Again, it is 3. So 3 into 3, we'll get 9. Okay. Now for the M plus 2 peak, there is two probability. In the first case, for the ratio of chlorine 37, it will be 1. So 1 into, and the ratio of chlorine 35, it is 3. So 1 into 3, it will be 3. Now the second case, chlorine 35 into chlorine 37. So chlorine 35 means 3 into chlorine 37, 1. So 3. Now for the M plus 2 peak intensity, we should add both these ratios. That means 3 plus 3 will get 6. So the ratio of M plus 2 will be 6. And the last case, for M plus 4 peak, both chlorine should be in chlorine 37 form. And the intensity will be for chlorine 37. The ratio is 1 into second also chlorine 37. So 1. So total it will be 1. And now the relative ratio of M peak is to M plus 2 peak is to M plus 4 peak will be here 9 is to 6 is to 1. So it will be 9 is to 6 is to 1. In the options, the correct one will be option D, that is 9 is to 6 is to 1. Okay. Now we'll move on to next question, that is in the mass spectrum of dodecahedron, that is C20H20, approximate ratio of peaks at M by Z 260 and 261 is. Suppose here if you are taking 260 as M peak, 261 will be M plus 1 peak. So here they are asking for the ratio of M peak is to M plus 1 peak. So this we have seen in case of carbon. Because carbon can present in two forms, carbon 12 and carbon 13. And if carbon 13 is present, the M peak will increase to M plus 1 peak. And the relative ratio between M peak and M plus 1 peak in case of carbon 13 will be 100 is to N into 1.1. This you already seen. That is, carbon can be either carbon 12 or carbon 13. And for carbon 12 peak, we will take the intensity as 100% always because it will be the most intense peak. And now for carbon 13, if you are having only one carbon in the molecule, for it to be present in carbon 13 form, the ratio is 1.1. So if you are having n carbon in the molecule, the ratio will become n into 1.1. Okay. So now the ratio of M is to M plus 1. Here M corresponding to carbon 12 peak and M plus 1 is corresponding to carbon 13 peak. It will be 100 is to N into 1.1. Okay. Now we'll come back to the question. In question, we need to find the ratio between M peak and M plus 1 peak. That means we need to find the ratio in between carbon 12 peak and carbon 13 peak in the molecule. And in the molecule, for that, you need to find number of carbon atoms. Here we have given the carbon atom number is 20. So N here is equal to 20 and the ratio between M peak and M plus 1 peak will be 100 is to N into 1.1. Here N is equal to 20. So 20 into 1.1 and this will come around 100 is to 22. Okay. So here the ratio between M peak and M plus 1 peak will be 100 is to 22. But in options we have given 1 is to 1, 5 is to 1, 10 is to 1, 20 is to 1. So I want to reduce this 100 is 22 into any of this value. Here we can see all these containing 1. So this 22 we need to reduce to 1. That means 100 is to 22 will divide by 22. In this case, here we'll get 1. So in the M plus 1 side, we are getting 1. This is the ratio between M peak and M plus 1 peak. So M plus 1 peak, if we are dividing by 22, we are getting 1. And 100, if we are dividing by 22, we'll get around 5. So the ratio will be 5 is to 1. So the correct option here will be option B, that is 5 is to 1. Okay, here we have seen the ratio between M peak and M plus 1 peak using the relation of 100 is to N into 1.1. And now we'll move on to next question. And now we'll discuss one question from reaction intermediates and we'll wind up today's class. And the question is the intermediate A and the major product B in the following conversion are. So the first conversion is the molecule, this molecule reacting with sodium nitrite and HCl, and we are getting a product like A, and this A is reacting with this molecule and we are getting B. So in question we need to find out both A and B. So first what is happening here, we can see it is a primary amine which is attached to a aromatic molecule here, and it is reacting with sodium nitrite and HCl. We already seen this reaction. If you are having a primary amine attached to a aromatic ring, and if this is reacting with NaNO2 bar HCl, diazotization will happen. That means this NH2 group will convert to N2 plus, and this is a very good leaving group. And this conversion, we'll call it as diazotization reaction. So here I am writing the product of first step in this reaction. That is, this primary amine is reacting with NaNO2 bar HCl, and we are getting a diazotization product like we have a benzene ring, and after diazotization we are getting N2 plus from NH2, and adjacent carbon we are having a carboxylic acid group. Okay, and here the deprotonation will happen. That is, this molecule lost H plus and a negative charge will form on the oxygen. And this negative charge will come in between this carbon and oxygen. And in this case, this bonding electron will move here. So in this case, this N2 plus, it is a very good leaving group. It will leave with this bonding electron. So from the reaction mixture, the N2 or nitrogen gas will leave. So after this reaction, we will get a benzene from the molecule. So benzene means you'll have two double bond and a triple bond in the molecule like this. So after the reaction of this molecule with NaNO2 and HCl, we are getting benzene as the reaction intermediate. Okay, so in option A is carbocation, it is wrong. And in option B, A is carbanion, it is also wrong. And in option C, A is free radical. So option C also wrong. In option D, we can see A is benzene. So option D is the correct answer. And now we'll see the product also. In the product, that is to form the product B, the A product, that is this benzene, is reacting with this molecule. So here, if you are drawing this molecule here, we can see this molecule is containing two double bond. So we can call this molecule as diene. And we have seen in reactions of benzene, this bond is weak and it will participate in cycloaddition reaction. That is, it will participate in both 2 plus 2 and 4 plus 2 cycloaddition. And in both these cases, it will participate as a 2-pi system. Okay, this 2-pi electron will be donating from benzene. And now we have a molecule which can donate 4-pi electron because of the 2 double bond here. So here, the 4 plus 2 cycloaddition will happen. So now for the 4 plus 2 to happen, the diene should be in schizoid form, but now the die is in transoid form. That means both the double bond are opposite direction. So first, for the reaction to happen, it should convert to a schizoid form. Okay, so now we have diene in transoid form. So first, this bond will rotate so that you'll get a schizoid molecule from this, like this. Now we got a schizoid molecule, schizoid diene, and now it can take part in 4+2 cycloaddition with the benzene. So first we'll draw the benzene here. So this molecule is reacting with the benzene in 4+2 cycloaddition. So here what will happen? This bond, it will move here, and in this case this bond will move here, and this bond will move in between this carbon and this carbon. So after the reaction, this bond will break. Instead, you'll get a new bond here, and this bond will break, and you'll get a new pi bond here. Okay, and now this bond will break, and you'll get a new sigma bond here. So after the reaction, we got a 6-membered ring here. Okay. So the reaction product will be, we already have a 6-membered ring in benzene before the reaction itself. And now a new 6-membered ring formed after the reaction, which is having a double bond here and a CH3 here. So this will be the product. So now if we are going back to the options, we can see this is the product that we are getting. Okay. So in this question, the correct answer will be option D. That is, after the first step, we are getting a benzene, and after the reaction with this diene, we are getting the 4+2 cycloaddition product as this. Okay. And with this question, we are winding up PVQ discussion of organic chemistry due to the time constraint. But if you are facing any difficulty while solving the question, you can contact me. And I hope you all understood what we have taken in today's class. And thank you all.